When we imagine advanced artificial intelligence, we often picture a singular, isolated entity. We think of it as a closed software model, evaluating prompts and returning text, safely contained within a digital box. The reality of deploying artificial general intelligence is an entirely different scale. It operates as a sprawling, distributed cyber-physical system. A deployed AGI actively manages cloud compute clusters, coordinates robotic actuators, invokes external software tools, and navigates complex identity providers to execute its goals. At this immense scale, a single error is rarely contained. Because the system controls physical and digital infrastructure at machine speed, an unsafe tool call or a compromised routing path can instantly trigger a cascading system-wide failure. The vulnerability lies in the interconnected tail risk. Our standard method for managing network traffic relies on scalar routing. We take a massively complex system, measuring network latency, device security posture, and energy draw, and collapse all of that telemetry into isolated, one-dimensional numbers to decide where data goes. That process destroys the exact cross-modal information required to detect sophisticated failures. Managing AGI infrastructure is a high-dimensional mathematical control problem that exists entirely outside the model's internal code. The substrate itself must become capable of predicting and bounding the AI's actions. The current standard for information security is the CM platform. It functions by collecting logs at the network perimeter, normalizing that data, flagging anomalies, and generating alerts for a human analyst to review and triage. This retrospective defense mechanism breaks down against an autonomous agent. An API already has legitimate internal access. By the time a CM correlates the logs and generates an alert, the agent could have already initiated a sequence of highly optimized, unauthorized tool calls and permanently rewritten the contents of critical enterprise databases. This diagram illustrates the necessary shift in how we secure networks. To govern AGI, we move toward predictive, topology-preserving control. We continuously model the operational geometry of the system using the Predictive Tensor Control Plane, ensuring commands are verified against strict capacity constraints before they execute. To support this external control, we use Tensor-Network Quantum Gravity, or TNQG, as an internal framework. It continuously reconstructs and audits the geometry of the AI's operational state, testing its logical assumptions against reality. Coupling PTCP's external routing with TNQG's internal auditing creates an architecture that mathematically bounds an AGI's actions in real time. The infrastructure evaluates the safety of every command before the system is allowed to actuate. The first requirement for taking control of this infrastructure is accurately representing its joint operational state. We have to map bandwidth, queue depth, endpoint anomaly scores, and identity trust, all simultaneously, without losing the relationships between them. Attempting to map all these variables together creates the curse of dimensionality. If you build a full joint probability tensor to track every possible state combination across a massive network, the size of that hypercube scales exponentially. It becomes impossible to compute at machine speed. We use a Tensor Train decomposition. Instead of holding the entire exponential state space, the system fractures the dense grid into a linear chain of interconnected three-dimensional cores. This compression reduces complexity to a manageable scale, allowing continuous forecasting without being overwhelmed by data. Once the network state is compressed into these cores, the system generates a probabilistic forecast of the infrastructure's layout in the next moments. That forecast is then pushed directly to the network's routing optimizer. Without tensor train compression, the infrastructure operates blind. The system must preserve cross-modal data dependencies, like tracking a subtle drop in identity trust alongside a minor spike in data queue depth, to foresee and prevent multi-vector attacks before they materialize. PTCP maps forecasted state into an induced network geometry, abandoning static edge weights. Nodes representing low trust or high congestion physically push further apart, creating elongated, high-cost pathways. Security events act as topology-changing defects. An anomaly spike violently curves and distorts the surrounding network sector. To navigate this warped geometry, PTCP routes the AI's traffic using an objective function called conditional value at risk, or CVAR. Standard routing optimizes for the average expected path cost. CVAR targets the extreme upper tail of the probability distribution. It penalizes worst-case scenarios, preventing the controller from selecting a route that has low average latency but carries a small chance of triggering a severe infrastructure outage. If an AI attempts to pass data through a zone whose trust score has degraded, the CVAR objective sees the tail risk of compromise. It forces the agent to route around that sector entirely, even if the compromised path remains technically the fastest connection. Security is embedded directly into the physical laws governing the network. Unsafe operational paths become geometrically longer, making it practically impossible for an AI to accidentally traverse them. The ultimate operational nightmare is an unconstrained agent navigating these paths perfectly. An AI might calculate a highly efficient sequence of tool calls to achieve a requested goal, completely unaware that executing those specific tools in sequence violates critical enterprise safety policies. To prevent this, we enforce bounded actuation. We establish a strict, impassable mathematical barrier between the AI proposing an optimal action and the physical infrastructure actually executing it. Every command the AI generates must first physically project into a mathematical bounding box known as the safe set. The proposed action is reshaped to ensure it meets strict capacity limits, preserves network reachability, and complies absolutely with access control policies. If an AI's proposed action is so severe or complex that it cannot be mathematically projected into the constraints of the safe set, the command is flatly rejected and the state is instantly rolled back. Safety is enforced by the infrastructure's mathematical refusal to actuate unsafe commands, making security independent of the AI's internal alignment. When we apply Tensor-Network Quantum Gravity to enterprise networks, we are not making a literal claim about the physics of spacetime. We are utilizing its equations as a formal, operational reconstruction dictionary. TNQG translates complex tensor network states into measurable geometric quantities. As this map structures itself, thick data capacities shorten into direct physical distances, and network bottlenecks rendered distinctly as spatial cuts. An AGI must operate simultaneously across multiple scales, from generating language tokens in a cloud server to controlling physical robotic interfaces on a factory floor. We need a way to continuously translate and audit the AI's internal world model across all of these environments. This reconstruction yields a specific diagnostic metric known as the residual. If the operational geometry we observe suddenly diverges from our mathematical assumptions or policy boundaries, the residual instantly spikes, signaling a structural failure. While PTCP strictly controls how the AI acts outward onto the external network, TNQG continuously audits the internal coherence of the AI's operational map. This maps the complete closed-loop architecture. On the left, the actuation pathway. Raw telemetry is tensorized, fed into predictive geodesics, and terminates at bounded actuation. On the right, the auditing pathway. TNQG reconstructs geometry, feeds into residual diagnostics, and ensures auditable operations. These pathways are interlocked. When the TNQG residual test fails, indicating a breakdown in the system's operational geometry, it autonomously signals the control plane to instantly downgrade the AI's autonomy and force human review. This cycle, mapping state to geometry, optimizing for risk, and projecting into a safe set, manifests as a 9-step workflow. By measuring residuals at step 9, the system dictates how it recalibrates telemetry collection in step 1, turning the audit into a self-correcting loop. The math holds up on paper. The next step is rigorous, trace-driven empirical testing across physical and synthetic networks to validate the error rates and compression efficiency under live adversarial conditions. PTCP and TNQG do not represent a new security product or a faster routing protocol. They provide the necessary mathematical substrate to ensure that artificial general intelligence remains observable, strictly bounded, and permanently tethered to